Okay, so let's look at practice test number 1. This is number 7. And this is another physics problem. So in this one, they give you the position function, and s is in meters, t is in seconds, and the first question is, find the average velocity. So let's do that. Now, we know that velocity, instantaneous velocity, is really the derivative of the s with respect to t. So that's instantaneous velocity. Instantaneous. So if we want average velocity, instead of taking an instant derivative, we want this would be like slope of a tangent line. Instead, what we want is going to be the slope of the secant line. So that's delta s over delta t. And we want the average velocity during the first 2 seconds. So that's the same thing as s of 2 minus s of 0 over 2 minus 0, right? Because that's my change in s over my change in t. So if you actually plug in 2 into your function up here, you should get 1/3. And if you plug in 0, you get 1. And that's all over 2. And then if you simplify this, you're going to get negative 2/3 over 2, which is negative 2/6, which is negative 1/3. And our units here are meters per second for velocity. So that's part A. Part B says, now find the instantaneous velocity at t equals 2. So that's actually, now we take the derivative. So v of t is going to be s prime of t. And let's see, if we take the derivative of s of t, we're going to get negative t squared plus 4t minus 3. And we want the velocity at 2 seconds. So I'm going to plug in 2 into s prime. So that's going to be negative 2 squared plus 4 times 2 minus 3, and that ought to come out to be negative 1, and units, meters per second. Okay, so that's part B. Part C says sketch a graph of V, and it gives you the window to use. So let me pull up the calculator here, and I'm going to clear all this stuff out. So let's see here. We need to sketch V. So V is the derivative of S, which we found, negative x squared, really it's t, what is it, plus 4t minus 3. And so I can graph that. You could also do it by putting y1 as s of t and then y2 using n deriv of y1, and then just turn off y1 when you graph it. But since it's relatively simple, we can do it this way. And so, oh, let me adjust the window. So let's see, it's from 0 to 5, and from negative 5 to 3. So here's our graph. And what I think I'll do is I'll actually just copy this graph directly. So edit, copy, paste. Okay, so there's my graph. Right there. So that's part C. And let me put V of t here just so I don't forget what we're looking at. And this is t. Okay. So when does the particle move to the left in the negative s direction? So moving to the left, the idea is that it's moving on a number line, which is whatever the s is. So moving to the left would mean the same thing as if this is a number line, just s, then moving to the left would be going backwards, right? So moving backwards. And moving backwards is the same thing as saying velocity is negative. So what we need to do is figure out, well, when's the velocity negative? And you can see from the velocity graph that we just came up with that the velocity is negative here and here, right? So what that's saying is velocities, and you can even see where the intersection points are. You could solve for them by factoring out this thing. And you're going to get that this happens at t equals 1, and then it crosses again at t equals 3. And so it's got a negative velocity from 0 to let's see, to 1 second, and again from 3 seconds all the way up to everything, so in seconds, because it just keeps moving backwards. Are we limited on how many seconds? Nope, it says just keep going. So okay, so that's C. Or D. E says, what's the acceleration at the times when the particle changes direction? Okay, so let's do this. E, I'll switch back to black here. So particle changes direction. What that means, the way that we can interpret that is, well, if it's moving left and then it switches to right and then it switches back to left, that's the same thing as the velocity changing sign. That's the way to interpret that. So, you know, if we make a little sign chart for velocity, I know that we got to start at 0 seconds. I know that at 1 second it has a 0, and that at 3 seconds it has a 0. And you could plug in test points, but we have the graph right in front of us. I know that from 0 to 1 it's negative, from 1 to 3 it's positive, and from 3 on it's negative again. So v of t changes sign at t equals 1 and t equals 3. Now, you didn't have to do the sign chart if you're staring at the graph anyway, but it's useful to get used to that anyway. So let's see here. We need the acceleration at these times. We need the acceleration at time equals 1 and the acceleration at time equals 3. So in order to get the acceleration, we need to take the derivative of the velocity, which is the same thing as the second derivative of the position function. And so we have that here. This is what we need to take the derivative of. So if I take the derivative of that, I get negative 2t plus 4. So that's my acceleration function. And if I plug in 1, then I'm going to get negative 2 times 1 plus 4, which is 2. And that's going to be meters per second squared. And if I look at 3 seconds, I'm going to get negative 2 times 3 plus 4, which is going to be negative 2 meters per second squared. So there's my A of t at those 2 times. Let's see, what's next? Where on the number line on the s-axis is it when it changes direction? Okay, so F. Since we're trying to figure out where it is on the number line when it changes direction, S tells us its position. So, and we know that it changes direction when the velocity changed sign. So that was at t equals 1 and t equals 3. And so we need what S of 1 and what S of 3 are. So S of 1, if you plug it back into the original function, it's negative a third, 1 cubed, plus 2 times 1 squared, minus 3 times 1, plus 1. And that equals negative 1/3. And the units on the for S was in meters. So it's at negative 1/3 on the S number line right here. So here's negative a third, let's say, meters. This is S. And then at S equals 3, it's negative 1/3, 3 cubed plus 2 times 3 squared minus 3 times 3 plus 1. And that comes out to be 1 meter even. So right here, this is at t equals 1. And let's see, at 3 seconds, it's at 1 meter. So let's put that about here, 1 meter. That's at t equals 3 seconds. Let's see, what's next? Okay, what's the average acceleration from t equals 1 to t equals 5? Okay, so instantaneous acceleration is the slope of the tangent of the velocity graph. That's instantaneous. So instant acceleration. If we want average acceleration, then I don't want to take the derivative of v. I don't want the slope of the tangent line. I want the slope of the secant line. So I'm going to take a regular slope instead. So it's just the change in the velocities over the change in the time. And we're looking at from 1 second to 5 seconds. So really what I'm going to do is v5 minus v1 over 5 minus 1. That'll be the average acceleration. So v5, if you actually plug in 5 into the velocity function, which is, where's that one? Right up here. So this is my velocity function. If I plug in 5 into that, you get, let's see, negative 25 plus 20 minus 3. So that's going to be negative 8. If you plug in 1 into the velocity function, you'll get negative 1 minus 3 plus 4, which is 0. And then all that's going to be over 4. And so this just ends up being negative 2. And since it's an acceleration, it's going to be in meters per second squared. Okay, hope that helps.